Okay, so we have an object inside the focal point. The first ray is drawn parallel to the principal axis, and then it bounces off the mirror and goes through the focal point. Remember, there's lots of light bouncing off of your object, and so that's just one of the possible rays. Now the second ray is in line with the focal point. So line your ruler up with the focal point at the top of the object. Draw a line that goes from the top of the object to the mirror, but then it bounces out parallel to the principal axis. So like about this. The third ray, line up your center of curvature and the top of your object. Again, you're just going to draw a line from the top of the object to the mirror, and then it bounces right back on itself like this. Now if your eyeball is over here, your eyeball is not going to ever see these rays converge on the left side. But what your eye does see is what appears to be a ray coming from behind the mirror. Now don't draw that as a solid line. It needs to be a broken line because it's a virtual ray. There's really nothing behind the mirror. And again, this blue one, you can draw its virtual ray. Again, making it broken there. Your eye would see this guy, looks like he's coming from back here. Oh, and if I was an awesome drawer, I bet all three of those rays would cross each other. They don't quite cross each other because I didn't do a very good job drawing them. But your eye sees an image formed where these three should be intersecting. So I'm going to make it about right there. So there is our image. Now this image is upright. It's enlarged. And it is a virtual image. It's not really there. Let's do the next one. Alright, so for the third one we have a convex lens, and our object is out here in front. We're going to draw our three rays. Now the first one should be parallel to the principal axis, and then it is reflected in line with the focal point. So take your ruler, line up the focal point in the intersection of that first ray and the mirror, and draw a line that goes from the mirror out up and to the left there. Make this portion right here your broken line because that is not really there. Let's do another one. So the next ray should go towards the focal point, but it hits the mirror and bounces off parallel. So I'm going to erase this portion right here. Again, I was just trying to get it in line with the focal point. And then we're going to bounce off as parallel as possible here. And then my third one, from the top of the object to the center of curvature and then back on itself. So again, you don't need this piece back here. So when your eye is over here, it never sees these three rays, this first, second, and third ray, ever cross each other. But it appears as if the red ray is coming from a place behind the mirror over here. So make that a virtual ray. Extend that ray back so that it's dot, 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 virtual ray. Same thing for the blue one. So extend the blue one back here too. Again, it's a virtual ray because it's not really coming from behind the mirror. So there we go. And then where they cross, and I did a better job with this one, my little image will be formed. So this image, so it's really a tiny arrow. There you go. It is upright. It's reduced. and it's behind the mirror, so it's virtual. Now, because of the nature of spherical mirrors, the focal point is located at 1/2 of the radius of curvature. Now, if we look at a image object pair, so here was an object, and here is a resulting image, and this is where the mirror was located, maybe. And now that I know where the image is, I can draw any ray I want to, because I know where it is going to start, and I know where it must go to because I know where the top of the object is. So we have discussed the distance between this object and the mirror as being our DO, and the distance between the image and the mirror as being DI. Now, because this ray hits the mirror and bounces off, and it's at this little tiny intersection where it's almost a plain flat mirror, then this angle here, theta, is equal to that angle there, theta, even though they're not drawn that way today. So if I look at these two similar triangles and call this HO for the height of the object, and this is HI for the height of the image, then I can make a similar triangle relationship but using the tan of theta, which is the angle that the incident ray makes with the normal to the mirror. So tan theta would be opposite HO over adjacent, which is DO, and tan theta for my small triangle would be opposite HI over adjacent DI, and this is negative because that image is upside down. And if the thetas are the same, then HO over DO would be equal to negative HI over DI. If I get the heights together and the distances together, then DI over DO, negative on the left side, would equal HI over HO. So the ratio of the height of the image to the height of the object is the magnification. Alright, so we should be able to come up with a relationship between the image distance, the object distance, and the focal point. So let's look at that diagram again. And now let's take our, so here's our mirror. And let's say this is our image here, and here was the object here. And the center of curvature would be somewhere like right here. Now let's remember there's a ray that goes from the top of the object through the center of curvature and then back on itself. So if I'm using that ray, then this angle and that angle must be equal to each other because of vertical angles. This is still HO. This is HI. This distance right here is the radius or center of curvature distance, and this distance right here is DI, and this distance here is DO, which makes this guy right here DO minus R for the base of this triangle, and this right here is R minus DI for the base of that triangle. So I'm going to do the same thing with the tan. So the tan of theta would be HO over DO minus R, and tan theta for the other triangle is HI over R minus DI. Again, tan theta is equal to tan theta. So HO over DO minus R is equal to HI over R minus DI. So let's, now HI over HO is equal to DI over DO. And HI over HO would also be equal to R minus DI over R minus DO. So that would be DI over DO from the magnification relationship. So then just looking at this piece here, DOR minus DIDO is equal to RDI minus, but I need a negative sign right here, which makes this negative, this positive, DIDO. Okay, so then DOR minus 2 DIDO is equal to negative RDI. So then DOR plus RDI is equal to 2 DIDO. But if F is equal to R over 2, then R is equal to 2F. So DO2F plus 2F DI is equal to 2 DIDO. Grab a lightsaber, divide by 2 on both sides, and then we'll have DOF plus FDI equals DIDO. Alright, so that doesn't look pretty, but it's getting there, I promise. Let's divide both sides by F. So then we'll have DO plus DI is equal to DIDO over F. Now I'm going to divide both sides by DIDO. DIDO is off to work we go. I'm just kidding. That was for Ismar. I hope he's listening. Hey, wait a minute. When I divide by that side, doesn't that just erase out? Okay, good. Sorry, kids. 1 over F. Okay, so then DO over DIDO would just be 1 over DI, plus DI over DIDO would just be 1 over DO, equals 1 over F, and there, put a box around that sucker. Now you know where the mirror equation came from. Yay! Now, in order to use it properly, we have to define some signs. So when the magnification is greater than 1, we have an enlarged object. When the magnification is less than 1, we have a reduced object. When the magnification is equal to 1, it's the same size. Yay! When the magnification is negative, the image is inverted. When we have a positive magnification, it's upright. And I'll tell you a secret, an inverted image is always real. An upright image is always virtual. Now for the focal lengths, we have a positive focal point for a concave mirror and a negative focal point for a convex. And
good afternoon.
A positive image distance means the image is in front of the mirror, and a negative image distance means the image is behind the mirror. And that is all.